Guys, how are you? Good. Yeah, like to extend the audio.
Just right now,
Let me start.
well, I'm gonna start with your bio.
Yeah, go ahead. Yeah.
But since I'm getting to use this thing, so I can't really down a bit. I have to give you a warm welcome, right?
Thank you.
Thank you.
Oh, see ya. Okay, have a good day. Have a good evening. Take care, guys.
Okay, have we got the Zoom people on? Yes. Everything's ready to go? Great. Thank you so much. So it's my great pleasure today to reintroduce Bruno Kamdem, who spoke at the Peter Carr Memorial Conference. For all of you saw his very nice presentation there, and agreed to come in and give us some more of this flavor of the future of finance, in my opinion, and hearing more and more about ESG, responsible investing, carbon credits trading, and this is getting to be quite a hot area. And I would think 5 years ago, I wasn't paying that much attention to it, but now because of you, we're starting to become interested in it. And so thank you very much for coming to speak. So the title of the talk is going to be Reinforcement Learning Mechanism for Trading Wind Power Futures. So hopefully we'll talk about wind and all the damage that the birds do. And that's a different story. Anyway, Bruno's bio, he's an expert in climate and energy finance, quantitative science, consultant and educator. He's currently an adjunct faculty at NYU Finance and Risk Engineering. Bruno is a co-founder and principal of startup actuarial consulting firm where he leads strategic initiatives to assess and report carbon exposure and climate performance. In that capacity, he also leads the development of emerging ESG market bond indices, afforestation efforts, and green bond solutions in various jurisdictions in East and Central Africa. I've reviewed his very long scholarly resume, but he did obtain his PhD in operations research from George Washington University and MS and BS from University of Maryland. So welcome very much. We're so happy to see you.
Thank you, David. I really appreciate the introduction, and I equally appreciate you. I always remember when I taught the commodity class at Hopkins, and I saw David name, one of the first work on commodity hedging and pricing many years. Thank you, David. Yeah, and I also want to thank the department and everyone here and for naming this seminar called seminar, which is really great. And it was this work actually is a consequence of empowering me to teach ESG investment here at NYU. So it's an ongoing work. It's very exciting because it's a big even in among the practitioners as well as for among academics in different university. So we're gonna today talk about this reinforcement learning. Okay. Okay, so what next? We're going to look at some of the issues at hand going on in Europe, which is making trading wind or electricity very hot at the moment, particularly in Europe. We're talking about the machine learning approach to what we're doing, and then formally and present a very important theory that's going to be told to this work. And later we'll talk about some implementation. And here we use mostly Python as an implementation tool. There's some of the implementation of the work that we do. So first of all, as a result of the war in Ukraine, Europe is having to consider its energy security and reliance on imports from Russia. Many of us here what's happening with gas. So there is a short supply in gas, and as a result of that, the war is pushing or coercing many to invest in wind. Why? Because electricity generated from wind is increasing, right? It's separate. They don't have to rely on gas anymore. It's Russia is supplying that. So if you look at some of the recent data electricity generated from wind in the European Union increased a record of 13% from 311 terawatt hours to about 315 terawatt hour, according to recent report. So
But on that question, just curious, like right now, what percentage of the overall electricity of Europe does that comprise? Just curious, compared to what from generated from, let's say, like natural gas.
I think it's significantly high, actually even higher than what we have now, because you know, the supply of gas has been shut down by Russia, and I think I was listening to a news report that they're building some new renewable resources in wind to generate electricity, and I think the European Union actually is putting money, is giving money to wind power generator, who's an investor in wind, or company wind, to really increase their price and increase all the infrastructure needed to generate electricity from wind. So it is something that's going to go up and up, according to what they think, you know, and according to recent news. Another thing is, you know, you should think of electricity market. Electricity markets were originally designed to focus on conventional coal. So the fact that you have to rely on RDS, that's renewable energy sources, make it very uncertain, right? You make markets and those that participate in those markets vulnerable to limited predictability and to the increased variability associated with energy. This you see, you can see the uncertainty there. It's you get the narrow predictability of wind. It's very narrow predictability of wind. And you can also think about the intermittency of electricity generation. It can complicate decision making among traders. So yes.
What do you mean by narrow predictability?
Narrow predictability means that we can have more volatility, right? Given that wind is very uncertain, we don't know, it depends on the season, right? We get about season soon. We don't really know when it's blow, or you know, we see this. It's weather, it's nature related. Like anything nature related, it can be quite.
So except for very short-term forecasting, it's very difficult to.
Yeah, and it created some a huge amount of volatility in terms of the price of the electricity future, which we'll discuss later. So such exposure to uncertainty and volatility bring or uncertainty bring about price volatility and increase the cost of regulation to imbalance between market schedule and realized production. Now we look at the problem from the standpoint of a wind producer who is actively participating in both virtual and short-term electricity market. So we focus on the very simple market setup, and that consists of a day-ahead market, followed by a real-time market to settle energy deviation with respect to the day-ahead schedule. So this is just an illustration, right? We look at the producer, right? The sign input option on selling 100 megawatts of electricity at 40 kilowatt per megawatt hour. So at the time of maturity, what happens is that producer choose whether to exercise the option of not, right? Is he going to exercise the option or not? That's going to depend on the estimate of the day-ahead market curve, right? So let's assume that the price, the market price is expected to be at 30 euro per megawatt hour. Then the producer will exercise the option, right, to receive a payment of 4,000 as you can see, there. While you get the student payment of 4,000 euro, wow, let's look at the other possibility. Participating only in the electricity market will have led to a payment of 3,000 euro, right? So for a day-ahead market price, you get the day-ahead market price here, estimated at 50 euro per megawatt hour. The producer expect your higher profit if it does not exercise the option and therefore choose to sell this production in the market instead, right? And that's what we illustrate here. So an advantage of that will not have been available having you sign a future contract instead, right? He will not have that advantage if he had signed a future contract instead. So in that case, the opportunity to benefit from the increased price would have been missed, right? And this example just showed the benefit of trading option and the corresponding risk. In our case here, in our model, in our problem, we look at the trader, commodity trader, who's trading not only option but future, right? As a way to manage risk, right? By trading future, it can more mitigate risk, right? And that's why we take this example that by trading future, you can do option, but trading future can better mitigate risk, all the more as electricity for wind production is increasing possibly in the European Union. So the key question that we're looking at are when should the wind power producer decide to exercise the right? Right? And the second question, what's the best price at which the derivative can be exercised? And here again, the derivative can be an option or it's possible. Right. So here we're using reinforcement learning to train the machine to help us, right, or help the commodity trader, wherever that could be, answer these two crucial questions. Right? We have to train the machine. We're going to show exactly how that goes. And then we focus on the volume of electricity that traded today in day-ahead markets, right? We have to focus on that. Delivery is and many other characteristics of the day-ahead market. And we feed into the AI the different maturity needs, right? At which the various financial instrument approaches. And another advantage of using reinforcement learning is that it will help us understand the effects of wind power on market uncertainty and trading strategy, right? Wind is a force of nature, right? It's difficult to control that. By looking at millions and millions of data in the past, we can train the machine to help the trader, right? Make good investment decisions. So that's one of the other maybe unexpected advantage of this project, right? It's going to give us a lot of information. So now, before we get into a model, let's look exactly at what this machine learning is.
Sorry to ask a question, I'm a little bit confused. So we're talking about these are standard options, right?
Yeah, we're talking about standard option and futures.
So when you talk about choosing the time to exercise,
yeah,
isn't that like the European versus American kind of?
Yeah,
you know?
Yeah. So we mostly into the European, right? We in the European framework.
So why is it a question then when the option is exercised? Would it only be exercised if it's in the money at maturity?
And then we have to look at the wind too, because this is so you're talking about a future. And in this case, electricity future is mostly produced by wind, right? So if we can train the data to see what's happening in the past and at what time, what time were the best to exercise the future, contract on the electricity contract, then we can see the best time at which we can. So it's really not depending on maturity. We also look at the wind, because the wind here affects the availability of electricity, because the electricity is produced by the wind, right?
So then the pricing of electricity will be based on the lowest cost supply, right? I assume?
Yeah.
Whether it's coming from natural gas generators or from wind.
Yes.
And so if wind is
And
available, it's
wind,
going to be cheaper, but if it's not available, then gas is going to be cheaper.
Yeah.
So the price process will be something like, the minimum of the two,
Yes.
right? But it's still a European option on that minimum.
Yeah.
The other thing I have right through my mind is that, in electricity, you have these like unit contingent contracts. We can have futures or options based on, coming from a particular source.
Yeah.
Because what wind provider would use these contracts if they had to supply power and they didn't have the power to deliver it?
Yeah.
Is that
Yeah, that makes sense. If the wind supply power and then it appeared that the wind is not something is wrong with the system. Yeah, so we just have to revert back to natural gas. Yeah, to produce that electricity. Yeah, that makes sense. I think that's something we can definitely take into account. That's a good observation that we need to take into account. So it's important. Thank you. Yeah, so that's very approaching observation. Thank you. So here we just want to do a little overview of what's machine learning. Just one slide, and then we can go to reinforcement learning, right? So machine learning is just a subfield of artificial intelligence. We have supervised learning, unsupervised learning, and then semi-supervised learning, and then what we're really interested in, which is reinforcement learning. So what does reinforcement learning involve? Reinforcement learning is the science of decision making. It is about learning the optimal behavior in an environment to obtain maximum reward. Right? If you go back to what David was simply say, if something is glitched, the system producing wind is glitched, and you can get a cheaper maybe production from the gas that we want the gas. Right? It's an optimal decision with maximum reward, right? Although in our case, we really don't want to deal with any fossil fuel resources. We really want to just deal with wind, right? So that's what reinforcement learning is about. Learning the optimal behavior in an environment to obtain the maximum reward, right? It's involved in agent, right? You have to have an agent, right? Or the learner. We also need to have the environment, right? It's very important. The policy that the agent follow to take action. So the actions are very key in the reinforcement learning. We're gonna apply this in a model in a few minutes. That's one of the reasons why we're talking about it. So you have the reward function and the observation, right? So these are very key to reinforcement learning. So reinforcement learning is mainly based on algorithm. Reinforcement learning algorithm can be categorized as model-free and model-based, right? Model-free algorithm is not built on explicit model in the environment. In our case, we're going to discuss that later. We're going to talk about model-free in the sense that we're not talking about the future price as depending on any volume motion. But what we're going to talk about model-based income to make sure that the future price of electricity kind of follow some sort of geometric volume motion, right? But later in our discussion, right? So, and those model have to when it comes to reinforcement learning, most of the model, right, are related to MDP. That's the marker decision processes. It's a very important part of reinforcement learning. And modern-based algorithm in reinforcement learning they rely on building a model of the environment by sampling, like by sampling state, taking action and observing the world. Right, that's the model base, and we model that in a model in this paper, right, making sure that the price of the future, right, is geometric orientation. Now let's go into our model here. So once again, we should go back to the example. You were just interviewing this type of example. We consider a wind producer who is actively participating in both virtual, physical, and short-term electricity market, right? And he is interested, right? He's interested in liquidating large block of electricity fusion, right? We have the X1, the X2, the X3, these are volume, right? And we assume that the entire execution should be within a short-term horizon, right? T, right? This short-term horizon. And his main goal is to sell future, buy them, obviously selling efficiently as possible, right? We have the optimum maximum reward, right? So we have that definition there. A trading strategy or policy is a finite sequence of vectors, right? Pi, AK is we can think of AK here as the number of volumes sold or bought at the I feature, right? And AK here is represents a decision-making index or the action of the trader. You know, the action the trader, if you go back here, about action, right? Was like that. The action in the reinforcement learning model. So NI is the sum of those actions. It's going to help us get some important information. And the benchmark we use here is the BWAP, which is the volume weight average price. I guess the benchmark of using in our model. So again, this is we are in the problem formulation. Let's continue with the problem formulation. Here we have VIK, the volume of the I future trade and a K trading period. We define the market VWAP. VWAP once again is volume weight average price, right? For the I future of K trade as that, right? That's MIK. SIJ is the real market future price of I volume, right? The key trading period, right? That's what the SIJ represent. I here is this a term that allows us to track the volume of the electricity price, and K allows us to track the trading period, right? Time. Yeah, so these are tracking indexes. They're going to change in a few minutes, and then we define the I feature of the K trade for the trader. That's IK, and for a discount factor, we can define the reward for the I feature. That right, RIK, that's the reward, and the overall reward of a basket, or however we can call it, as RK, right? We have that still in the problem formulation here. Now we look at the policy, which depend on the action, right? Policy depend on the action, right? We have an initial future price S. We define the Q function, right? Q function of the policy as that, and the Q function of the policy at that, right? We have S0 equals S, that's the initial future price, and A naught equals A, that's the initial action as we defined earlier, and then we have the policy, right? And then we get the corresponding value function for this different policy, and we want to find the optimal policy, right? When we get to optimality, you can get P star for optimal policy, which is going to be a function of the initial price and of A, right? Which is remember that we defined A earlier as a decision-making index, right? The action of the trader, right? So now after this, we move forward. This is the problem formulation, right? It's very important in understanding. Is any other P here is the maximum amount of trade. That's P, maximum amount of trade, and N is the maximum amount of future, right? Which is a way of modeling reality. So now for this here in the methodology, we need to solve that equation there. Is this sorry. Well,
Bruno, can I ask a question? Bruno?
Yes, yes.
Just if you go to the next page, I'm sorry, not next. Forward, just forward. No, I'm sorry, forward. I'm sorry, forward. So what you're sort of saying, you're starting off with an existing long position across the contracts, right? And then what you want to sort of say is how much should you sell of contract I at time period A?
Yeah,
Correct.
yeah.
So you're going to sell down over a
Yeah.
fixed amount of time, and you want to know how much you should sell at each time interval of each contract, right?
Yeah.
I'm just wondering, just think about it very naively, right? Seems to me like since they're co-movement in contract prices.
Yeah.
Right, you would think that to really solve this problem, you have to make some assumption about how they co-move. I mean, what I mean is, let's say if like, let's say you decide to wait and sell the next instant, right? Well, if one of them goes down, there's a high chance the others will go down too.
Yeah.
So you miss an opportunity to sell it up. So isn't the co-movement something have to be incorporated?
Yeah, that's the point. That's the first point. That's why those future price or contract are correlated. As I mentioned, there's a correlation, right? So we take that into account. Yeah.
Okay, but you said, are you going to model the way that are you going to put because the calculate model for how the prices move? Are you going to? It's model free. So are you going to assume a certain diameter process for each of the future prices?
Okay, for the model free, we're not going to care about that. For the model base, yes, we're going to have to care about that. We're going to have to track the behavior of this prices and see how they affect each other. Yeah, that's for the model base. We talked a little bit about the model base issue, right? So it's some very important. So here, this equation here, this one, this.
Well, yeah, but then what is the? I'm sorry. Is TIK actually capital T or times? Intermediate time?
No, the TR.
How much?
Yeah.
Trader speed.
Yeah, that's a trader of EWAP. So of the I features. So if you remember, we talked about the weight, the volume weight average
But
Right.
that's historical, that's historical?
Yeah, it's not the time, it's not the time. So, it's definitely not the time. So here, so this equation here, so this equation here is not a very trivial equation as it here. It's complex. So this equation, we need to go back and look at the work of Bellman. We look again, we look at any of the Bishop Bellman, some kind of father of modern dynamic programming. So we use that Bellman equation, right? And we introduce the last function, which is the expectation of the reward, and we have the discounting factor and of the policy Q, right? And you see that the policy, they are function of S, A, or some sort of action and take that. Now let's let's now look at the model-based approach, which is somehow what talking about earlier. So in this model-based approach, right, we have to look at the price of the volume, the electricity, right? We need to look at that. And AI here represents something else, right? AI K represent the number volume so of the I future at K trading period, right? So that's AI, and then we have to introduce this function here. Let I hope that see whether I can. Okay, sorry. So it's not okay. Yes, once you click that, that's why. So yeah. So I said first on it. What's this? Yeah. Okay, so. Just the right. Okay, so we're going to okay, here, right? This function fi is very important function, right? It captures exactly what the Theorem was talking about, the impact of those prices or selling or buying those futures, right? Fi here, the impact of selling or buying activities on those future price of electricity. That's what FI model here. To go back to your question, and that's why those SI are correlated, and sigma ij is the correlation, right? Is if you represent the sigma ij represent here the covariance of the future prices, right? So this is the model-based approach where we assume that the price follow a geometric motion, right? So and then we have to make this assumption. Remember that it's supposed to benchmark the weight price, the volume weight price of the volume weight average price. That's a benchmark there. That's we have to make that assumption, and then we can finally come up. Yes.
So regarding non-negativity of futures prices, electricity, it's very, very common to have negative prices. You know, in places where you have like nuclear production, almost every night you get negative prices for electricity, you know, for certain hours. So I'm not sure if we need to make the constraint that it has to be non-negative.
Yeah, I think you made a good point, and I think we assume negative price. We assume negative.
So this is the price of power, right?
Yeah.
Okay, but
Yeah.
then because I think the research is only on mean, is there a negative price on mean as well?
So I don't have as much familiarity with wind, but if there was forced production that you couldn't get rid of, You can't just discharge into the ground
Yeah.
anymore,
Yeah,
right? You have to sort of pay a cost to.
And-
dispose of it, you know.
Professor Shuko is correct, because the wind here, the electricity is produced by the wind. So really, we're looking at the electricity price issue, right? So we need to account for that negativity, and we do. We have to account for that.
And then the VWAP you're using, I mean, the average, but each average is that, I mean, like a month's average, it's like a.
Just the weight average. I think I'll come back by the end, because when you come to the practitioner, there's certain average that they use. I will ask you a question by the end of the presentation. Right, it's a good question, because they don't use any average when they trading future electricity future in Europe. The volume is like 20%, right? So the average is different. Right? So it's really different. Yes, we account for that negativity, which is very much. Yeah. So now we arrived at this theorem here, which is the key theorem, which allows us to implement a model in Python and using reinforcement learning, right? Here we have the value function, which is WN, right? Now we can get M. M is a very important coefficient, right? And here is kind of N capture. I would say I want to talk about lambda. Lambda. Now, M is just the volume, right? It's just the volume. I want to talk about lambda. It is some sort of control coefficient for the trader. If you know, everybody, you guys know that if the trader sell too much future, the price includes the market. But that's what lambda capturing, right? So we're able to get our optimal reward and our optimal policy, even C. C is just a positive number, right? So we use this to implement for our model, and then we can derive the application, but we need to have a lot of data. We mostly use a Python library called TensorFlow, right? It's pretty popular. You should go to GitHub, right? GitHub is several that going on there. It's one of the main libraries when it comes to reinforcement learning. But as you guys know, when you're doing a data AI project, you need a whole lot of data. Thankfully, Professor Jim connected us with guys in Europe. He has access to millions of data on electricity versus spot price, and mostly generated by wind. Mostly in Germany, right? We got in Germany, we got this data. The proprietary data, but we're able to get them. We're not going to share them with just like Alex sent an email recently, has a lot of data. I asked him to share that. He said he can't because they proprietary data. Same thing here. So we feed this data into the model because we need to have not only 60,000 data, we need to have even more updates. We need to have hundreds of thousands of data when it comes to AI, because we train the machine to do something, right? So we need to have a whole lot of data. I think that's what where we are at the moment, getting as much data as possible. Yes, Status.
I don't want to interrupt you about the data, but my question, it's more of a meteorological question, but
Yes.
I would expect wind to be very localized. So in some sense, there must be some basis risk between, where a wind turbine is located and where the wind is actually measured. Maybe it's measured in the airports. I mean, that might be something.
Yeah.
I'm just not sure. I'm just asking.
Yeah, that's a good question. I think it's possible extension of this way. I think there will be some way a risk. And I read some way with a podcast on The Economist. They have a podcast. What they call they went and got wind. They went and look at airports, in particular visual wind out from there, or how wind can be produced from different airports. But here we're looking at, we're really not caring about the origin of the source of the wind. We just want the wind as insofar as it can generate some electricity. And all the more so that right now in Europe is tremendously. If you look at the electricity feature, the most liquid markets, the American markets, simply that's what our research really is focused on the European market. Is the European market is very liquid feature. Electricity feature in the European market is very liquid compared to the American market. And that's why we get data, real-time data, in order to not only to calibrate the model, but to get the proper model. So these are some of the conclusion of our model for the moment, the application. First, we're talking about EHT. EHT is very advanced in Europe. And I remember Carr last time when I presented, he asked a question why climate is not serious in the moment. EHT is not serious here. It's just because it's difficult question to answer. The company is getting serious now. I think institutional investors are already leading the way in forcing trader decision maker in finance to really start constraining other assets to EHT factors, right? And that's what I'm kind of want to specialize on, special and exploring. How can we constrain EHT environment, social government factor into other class, asset class, in order to have a sustainable environment or a sustainable life in this world. So that's why this work is a part of that whole thing. So here, what we did too was to introduce a parameterized approximate value function in the convolutional network, which has been part of machine learning, in which we specify the way as we saw and of the Q network at each acceleration. And then we provide an optimal training mechanism by continuing evidence seasonality in wind production as electricity cell exchange. Another step that we want to look at is how the wind will influence trading strategy, following an influence trading strategy. I think we should be able to have enough data. We should be able to train the machine and let the machine inform us of the past trading strategy and how they can prepare the future trading strategy. So that's a bit of explaining that we doing. It's got a question.
What kind of wind data do you use?
What kind of wind?
You said you're using the historical wind data?
Yeah. So here we're talking about the volume weight price, right?
No, I mean, you use like
Wind, say.
wind, movements. You're using data.
Okay, the wind, the data here, we look at the spot price of electricity future, but those electricity, that electricity is mostly produced by the wind, by wind power.
Also, you use the price to see how that affects.
Yeah. And I think we have we're talking to he have access to data. So Adam's about wind, where they're coming from, by sourcing wind from this side, we can get better result. And yeah, we're gonna get data, and that part we allow us to see.
Well, so you didn't, add like a climate update or something.
No, we didn't have that kind of data. Yeah, but he does how, but contact is how some data, just not data, and that's going to help us implement the second part of the project, right? Which is looking at how we can affect trading strategy paths. But this time, we just look at spot price of future electricity. But those electricity are produced mainly by wind.
Actually, that's like another project from using the old wind data to forecast the future rate, and the effect of that on the price of the.
Yeah, I mean, once you have your reinforcement learning code, I can code, you can tweak and see and add using flow that we just spoke about, and add that part and then see how things when we're done in the past and how we affected decision in the past and use that to inform the future, right? Like the historians say, one of the best ways to inform the future is in the past, right? Sometimes. Yeah, this is my longest presentation ever. Usually, yes, 10 minutes.
There are some of us who really appreciate, very good short presentations.
Thank you. Yeah, guys.
So one thing to think about, so I'm not sure if you're familiar with Richard Bowles' paper from 1984, Orange Juice Futures and Weather. Somehow this rhymes with that, right?
Yeah.
In other words, I could maybe predict the wind better by looking at these fluctuations in electricity price than trying to predict the weather. Does that make sense?
Yeah, that makes sense. So kind of having so that implied, but that makes sense. If we get the data on the spot price of the electricity future as produced by the wind, and it imply the wind from there. Yeah.
I'm still a little stuck though on the data because if you're measuring the weather at Hamburg Airport, right? Maybe that's the data point. You have the wind speed at Hamburg Airport. Is how much basis risk is there between the wind speed at Hamburg Airport and the wind speed on the coast 1 hour north of the Hamburg Airport? You know what I mean? So that would be again an interesting kind of data question to dig into.
Yeah, and actually the European Union, they just gave money. I think it's an organization that produces wind to find very spot producing wind. Because as you know, the winter is going to be rough, not only Ukraine. The reliance, the fact that Europe relies so much, 40% of their energy energy sources come from Russia. Right? When it comes to gas, everything, even the heat, they all come from Russia. Now they don't have that. They need how to develop new ways to provide not only electricity but the energy to the population. So that's why they found the wind technology is quite huge right now. The European Union is giving money to find better way to use wind, to source wind and then produce the electricity that the people need. Right? So you see, and that's one of the reasons why the future market for electricity in Europe is very liquid. It's extremely liquid. Yes.
Quick question. So I know that there was this famous result from the 20 years on Chris, where you take a particular known background process for the stock price.
Yeah.
You introduce an impact effect. How much does your trading affect the price? Right. Ultimately, you solve this upper control problem where you settle on the right strategy, how you can sell down the position over a period of time. Right. Are you sort of saying that instead of modeling the native process of the price and introducing an impact effect, as you trade, you augment the price impact. You're saying machine learning can do that in a non-model way, and you can tell you what the best strategy does. I own 50 units of each futures contract over the next year. So I look historically at how they move, and I find the best strategy sell down this period purely based on which strategy would have been the best in the past, and machine learning identifies it. Is that correct?
Yeah, you can do that. You can do that. So it's actually pretty cool, and that's why everybody's excited about machine learning. But I think the coolest part is that in reinforcement learning is that we have the model-based approach, right? A model-based approach is pretty more realistic than the model-free approach, right? The electricity price fluctuates, right? And that's the model-based approach. So I think comparatively to the model-free approach, I would say that the model-based approach is statistically likely to give us a better evaluation of what's going to happen.
Well, like I can look at the data and say, oh, trend is your friend. When these prices are going up, it's gonna go up for a while, right? That being the case, you see prices going up, you should just sell more.
Yeah.
Right? Now, I don't need machine learning, I would assume, to see whether the historical data suggest that relationship, or maybe there are more subtle things about the cold movement, let's say, that I wouldn't pick up on my own, but machine learning might. Maybe might identify, I think,
Yeah.
here, sort of.
Yeah. There's some sort of things like, okay, wind is a part of nature. If you know that in the past, in let's say in Frankfurt or Berlin, might have been or Berlin, let's say Berlin, wind speed is greater in November or December. For the past 20 years, it's been the case. So you're trying to model, if you buy a future, maybe that's gonna expire, say, 6 or 8 months from now in 1 of December, you say maybe 12 months from now. Looking at the past, you can say, okay, let me just buy this with the expectation that the wind is gonna grow at a higher speed next December, and they make money. Because in the past 20 years, that's what happened.
And the machine learning machinery is identifying that for you.
Yeah.
You would not necessarily discover that yourself.
No, you don't.
It's not even to do with that.
The machine learning is telling you that for the past 20 years in December, wind has been doing this, and future the future price of
Responded.
has been responding this way. And then you can just look at that. I think this.
Why couldn't you argue that's already incorporated into the futures price? I mean, natural gas has a seasonal, right, and according to maturity, and so does power.
Yeah.
So
Yes.
if you know that there's gonna be more production in December or November, the price should be lower, presumably, and so that should be seen in the forward curve, for the expiration that date.
Yeah, but I think natural gas has a bit better predictability than the wind. The predictability of the wind is very limited.
Yeah. No, I agree with that, but it's just in the principle, though, the idea that what you just mentioned could be known, where the futures prices for November, December would be lower.
Yeah.
Because of this extra wind.
Yeah. And I think you're right too, because it's going to take a while for let's say 70% of all the electricity ready to be completely produced. Probably it's going to take a while. But the moment it's just ongoing, given the urgency in Europe. But most of the time it's gas, even in America. Gas is really it's big, yes.
So I'm trying to wrap my head around wind as a variable, because it seems to me that it needs to be a continuous variable. And if you pick the peak wind speed of a day at the Hamburg airport, it doesn't tell me whether the wind is blowing for an hour, 5 minutes. So I'm a little bit stuck on how that translates into this. If you have any insight on it.
How would a futures contract even settle? How would you even settle a futures contract on wind?
Yeah,
I need to do it.
Yeah.
Like you, but
that's a good question. I think the way to look at it is
So it's fine.
pardon me? Well, there's a file next year. Yeah, there is one. Okay, just do all get that, okay.
yeah, it's a lot of that going on in Europe. The guy, the actual guy is trading wind. I mean, like wind is trading wind.
Trading wind?
Yes. Right now, Europe, the trading wind is new, but we're not looking at that here.
It's like
It's very
natural wind, or it's like
yeah. I know the guy, he's actually trading wind. We're looking for he's actually trading wind.
What is it?
Yeah, when you have, when you have like wind power, you have wind turbine, you have all that plasma that is also in Europe, and then you can from the past you can measure how much they're gonna use.
who buy them?
Yeah, they're trading wind. Yeah, but in this case, in the case of our project, we're looking only at electricity generated by wind. Right? We're not looking at electricity generated by gas, no, only by wind. So the movement of the wind essentially affect always affect the price of electricity on the model case or
The result page, like, I mean. What's at the end, I mean, what's I mean, was there any, I mean, like specific result you get from the, I mean, programming round?
Yeah, I think our results are not really definite because we need some more data. 60,000 data are gonna get into it. We need techniques, and I think we can get up to a million data to really get some definite results. It's really about best time for the trader and to exercise future, and then the best price, right? So that's really where our results will be where our result is specified on these two main factors. Yeah, we're going to need more data. I'm confident that we can get some more data, because when it comes to AI, the two main things, the coding, right? You have to formulate the model, it's very complicated, and then hopefully you can come up with some paper or some, it's like exercise. You might take my class and use for exercise. You come up with something maybe nobody has done, you find the result of the exercise. And then you have to implement it in Python usually. And to really get the result, you need to pull the data. Because as you know, one of the problem AI is sometimes data bias. If you don't put enough data, you get bias, right? And the only way to resolve that is as much data. And that's what we want to do. Yeah. Any questions?
Yeah. So how do people know like which electricity is generated by wind or by other source?
Yeah, it's
By the color.
you can, it's green.
Green there is green.
Yeah, the information side is available. Yeah. Yeah. Yes.
Follow up what Dave was saying, like, I had a student a couple years ago at Quant, and following a very simple idea. Like, look at the oil futures curve, right? So, I mean, do we find that when we've experienced, I don't know, a massive inversion, backwardation, let's say, over the next 6 months, does it typically burst back? Or let's say a period where the spot price goes up a lot, that generally associated to, let's say, a flattening of the curve, right? So I would assume there's some things in more quirkier futures markets where a lot of more second, third order, you know what I mean, behaviors that maybe you wouldn't identify, you wouldn't think about asking the question. You know what I mean?
So in commodities and energy,
You're the commodity by not me.
we have the stock price follows like a mean reversion process in general. Like you say, the price gets high, economic forces are going to want to pull it back down. Right? And then when it gets low, the opposite will happen and be pulled up. But the futures will anticipate that. So futures can still follow the market gap, even though the spot price is predictable. So this is I think a challenge for this paper. It looks like you have spot prices.
No, the data we have the bus spot price on the data.
Right, that's saying spot price, which is unit contingent, because you say it's zonal price weighted to the direction of a specific site.
That's what the
So you have spot prices by site.
Yeah.
Right, great data set. But the question that it seems you're asking is to futures.
Yeah.
Right, so do you have futures prices as well?
Yeah, that's no, we don't have future price in terms of data. We don't have future price.
So I guess my concern is there's that step of figuring out, based on this very really strange spot price behavior in electricity, how to properly price futures to begin with, even if you have a model that does that.
Yeah, we plan on one of the things we plan on calibrating. One of the things we plan on doing is calibrating a model using the spot price, and maybe the future price. If you get the data, we can verify the validity of the model using the future. Yeah.
And then your second point here is that if someone, let's say, invests in wind production in Germany, are they getting these credits?
The credit for not contributing to
Carbon
the carbon. That's another part of what we do, and I think that's the paper that I presented at the memorial, which is on the way of being published in the Journal of Finance, because it's becoming very hot even the offset, all the things that makes it an offset. Yes, they will get the credit because they are using wind. And they can use that credit either to make more money in the option market, the carbon option market. And that's a good question because recently, if you think like 2 weeks ago, Jim Carrey, I think they were talking about how can they from poor country where the impact of climate change is being very heavily felt. And they talk about auction market, the carbon market, of being one of the main sources of the money to help those developing nations fight climate change. So this offset, if the company in Germany is using wind to generate electricity, instead of contributing to the increase of carbon emission, they're going to get carbon offset, and they can go into the auction market and trade it and make money. Yeah. Yeah. Thank you. Just to do that second point that we can actually add a paragraph. Yeah. Last time I was here, we did about 45 minutes. And then
Do you have to pay overtime? So, do you have any questions from the online folks?
Oh, sure.
No questions online. Okay, great. Any other questions from the group? Great. Thank you so much for letting me in. So the JF, is that accepted or is it?
It's on the process of being submitted. We had a third author. She, German.
Oh, of course, yeah.
She know you is when I told the class at Hopkins, she recommended a book by Alex. I don't know, Alex.
Yeah.
And I know she knows me well.